So good morning, everybody. My name is Dario Trabucco. I'm a research manager at the Council on Tall Buildings and Urban Habitat. And what I'm going to speak today about is an ongoing project that the Council has been doing in the past 1.5 years, thanks to financial support and sponsoring and cooperation of ArcelorMittal. It's called the Whole Life Cycle Assessment of the Sustainable Aspect of Structural Systems in Tall Buildings. It's an ongoing project. It's due to completion by the end of this year. And this is one of the reasons why we're not going to show any actual results, because we are still waiting to hear some of the aspects to be completed. The objective of the project is a complete analysis to assess the environmental impacts of the structural system of a tall building, of the above-grade structural system of a tall building through the building life cycle. We will see what the building life cycle exactly means. By the way, Anthony Wood is also the PI of this research, and the co-PI. Mason Tabizazes has been working on this research for the past 1.5 years. Payam Barami was involved in the first year, and Mattia Mercanzin just in the second half of the research. So exactly what we've been hearing about life cycle assessment, what exactly this is about. Life cycle assessment is a scientifically recognized methodology that is aimed at quantifying and then assess the environmental impacts of our action. We can do a life cycle assessment of this conference. We can do a life cycle assessment to produce the microphone or a bottle of water. We can do the life cycle assessment of a complex product such as a building structure. It's important to identify the impact categories of the analysis that we are doing, and we will come back on this because it's really vitally important. And especially it's important to create the system boundary of the research, so to exactly describe what we are targeting to, what the research is targeted to, in order to be able to compare apples with apples. There are many steps in a life cycle assessment, but there are 3 very important things that has not to be neglected. First of all is to create a life cycle inventory. This is basically the recipe of what we are studying, of the object of our analysis. So if we want to make a good apple cake, apple pipe, we have to know the recipe and to know exactly what's the balance of the ingredients that we have to mix together in order to have the perfect pie. So this recipe has to be reliable, which means that we should be confident that what we're going to do is going to produce a good apple pie, and it also have to be complete. So we have to make sure that we are not forgetting something that might be important, but we may consider not important, but can actually be very important. Also, we need to set the system boundaries. So we need to decide and to communicate to our readers and to the people that's going to use the analysis what was exactly included in this. Because we want to compare apples with apples. So if we want to considering the whole life cycle of a building, but we don't include the recyclability of the structures after the end of the life cycle of the building, we are missing something that might be very important. And also it has to be inclusive, so we have to include all the life phases of the building. And then, again, this is very important, the importance of the impact categories. They have to be fair. So the result of our analysis should not impair one of the competitors straight from the beginning of the analysis. And they have to be objective, so they have to be based on numbers that can be compared. This is higher, this is lower. We can make a comparison between these numbers. This is probably going to be one of the, we have seen other very accurate and specific analysis of tall buildings and tall building structures. This is going to be one of the first analyses, and we hope one of the most comprehensive analyses. Yes, because we're better than the others, but also because life cycle assessment is a very, very new methodology. And this is also very important in understanding that the results that we are going to provide and the results that we saw this morning are not definitive. So life cycle assessment has been created, we heard before, in the 90s. It was imported somehow into architectural engineering at the late 90s. And this is a graph that shows the number of peer-reviewed LCA studies. How many times the word LCA was appearing in peer-reviewed papers in the title or in the abstract or in the keyword. And we went from almost nothing early in the 90s to really a booming during the last decade. So this is important to understand. The results that we are going to present, that we saw this morning and the Council is going to present in a few months' time, are based on the current scientific knowledge on LCA. Maybe the scientific community is still working very hard to define what's the best way to understand an LCA and what's the best way to make sure that all the numbers, all the ingredients of this recipe are included into the analysis. So the analysis that will be done maybe in 5, 10, 20 years' time might be very, very difficult. If you think about that, the scientific community has been disputing for decades or centuries about the thermal expansion of gas or gravity or other scientific disciplines. Life cycle assessment is the new kid in town in the scientific community. Also, what we are aiming to consider is the whole life cycle of the building and of the materials that compose the building. So what we're including in our analysis is the energy that went into the production of the material, the transportation of this material to the workshop where they have been assembled together, then the transportation to the construction site, the construction process itself, which is relevant from a certain point of view of life cycle assessment, for instance, water consumption. We are assessing the life phase of the building structure. So what is the impact of a steel structure or of a concrete structure on the life phase? And we're also including the end of life, which is not negligible at all, especially if you consider the recyclability of the materials. All materials can be recycled, steel can be recycled, concrete can be recycled too, but steel is transformed into steel. Concrete is downcycled, which means that the secondary products that you can create with the recycled concrete are not going to be concrete again. You can create ballast, you can create some kinds of aggregate. You cannot use, for right now, you cannot use crushed concrete to create new concrete. So we are trying to assess all these items of the life cycle. And it's very important to know the exact recipe for your apple pie. So in order to be sure to include all the materials and to include all the materials in a reliable basis, we reached out for each of the life phases that we are targeting and that we are studying, the leading industries, the leading firms in the tall building industry. So for the construction phase, which means the inventory of the materials, so how many tons of steel, how many tons of concrete, how many rebars, and so on, that go into the building structure, we reached out with a structural design inquiry, most of the leading firms in the market, so Magnuson Clemenci, Charup, WSP, Walter P. Moore, Skidmore, Owings & Merrill, Wade Linger, Halvorson, McNamara, Nishan, Thornton Tomasetti, Bureau Happel, and several associates. These firms were contacted, they were given an assignment to kind of designing a tall building structure for us with some given parameters, a floor plan, a height, floor-to-floor height, and so on. And they got back to us with the exact quantities that go into the design of such structures. So the inventory of materials that will be part of the dissemination of our activity is very important. Because, of course, these are not going to be ultra-optimized structure because we consider the real building, the 300 LCA case study in Chicago, and we use that building as a model for our simulations. So that might be better structures that can be made more effective if they are in steel or if they are in concrete or composite and so on. But the inventory that will be released is very accurate, which means that somebody else can apply a different methodology for the study of the life cycle impact of the structure to our building material, to our inventory of materials, so to be able to compare different methodologies also. The same attention was paid with the other phases of the construction of the life cycle of the building that are usually not included in most of the LCA analysis that we have been found in the literature. And this is the demolition of the tall building. So we reached out three of the leading companies in the demolition market of high-rise building, Brandenburg, Despi, and Taizé. And we've asked them to demolish, to provide us a demolition plan for the same building that was designed by the firms that we saw in the previous slide. So they got back to us with the energy that will be required for the demolition, with the quantity of the equipment that will be required for the demolition, and with the time that will be needed to demolish that building. And we had some very, very interesting results, and we're actually going to create a new working group on this because the demolition of tall building is still something relatively new. At the world exists right now about 4,400 buildings taller than 100 meters, and only 50 have been demolished so far. So we really are building something that we don't know how to demolish. Nobody will know how to demolish in a century or in 2 centuries the Burj Dubai or the Kingdom Tower. And one of the most interesting findings that we got from this initial analysis is, for instance, the time of demolition. Demolishing a building takes longer than the time that was spent on construction. So if the structures that we imagined can go up in 18, 20 months, that will take approximately 3 years to be demolished. This is especially true in dense urban environment where you cannot simply blow up a building, but you have to dismantle it piece by piece. You have to follow some regulations to prevent the spread of dust, the noise that the demolition creates, and so on. And of course, if you build this in concrete or steel or composite, you have different impacts because materials can be demolished, crushed, or dismantled and dismounted. So all these things go into the equation. And the recycling, of course, is very important. So we reached out the world steel for numbers and information on the actual recyclability of steel, Acme Materials and Bluff City Materials, that are 2 contractors, 2 recycling companies in the Chicago area. And we asked them to assess what's the impact of recycling this. As for instance, also this was very, very interesting. We were told, yes, we can accept all the concrete that you will produce by demolishing the concrete scenario that you analyzed, but this will basically create the collapse of the concrete recycling structures around Chicago for the whole duration of the demolition. So the recycling of concrete right now is so marginal that there is not the infrastructures, there are not the facilities that can accept the crushed concrete coming for such a tall building. So these are all aspects that architects and engineers and consultants have to consider while they design their new buildings. Sooner or later, this building will need to be demolished. So the life cycle assessment performed is based on the ISO norms that were mentioned before. There's a complete handbook that was created by the European Community Joint Research Center that describes all the except part of a life cycle analysis and everything that you have to consider while doing a life cycle assessment. And then, of course, we use the software. There are many commercial software that are available out there. We use Gabi, which is the same software that is integrated into Tele. We considered all these phases. For the production of materials, the production and construction of the building, so the bottom line of all LCA analysis. We consider the production of the structural materials, the fabrication, the transportation to site, the construction of the building structure, which means the energy input that goes into the construction site and what are the outputs of that. And we acquired all this information, as explained before, with through this panel of experts that contributed significantly to this research. The same happened for the life phase of the building. So what we are considering is the durability of the structures, which means how much modification you can do. This may be, again, sometimes not considered as an important matter in a life cycle assessment, but we are seeing more and more buildings that now need to be readjusted to make, to maintain the value on the market. Buildings that were originally conceived as office buildings that then become hotels or residences, apartment buildings that are transformed into serviced apartments and so on. All this modification have an impact on the structure of the building. So there are certain kind of structures that are more keen to be adapted and transformed. There are other kind of structures that are more fixed into stone, so are more difficult to be transformed. We've been hearing a lot about the thermal inertia of building structures, and we are considering this, even though the initial findings show that this is not as important as we expected it to be. Of course, because all structures are very heavy structures, so the actual properties of the materials are not that relevant from this point of view. And again, the ratio of the gross to net area. Large structural elements occupy space that cannot be used for the building purposes. So if we use a structural system or a structural materials that requires larger structural elements, we'll probably need to build an extra floor or 2 extra stories in order to have the same net rentable area than a shorter building. For the demolition phase, we only consider, so basically we consider 2 scenarios for the life cycle inventory, a 60-story and a 120-story scenario. For the demolition phase, we only consider the shorter scenario because we understood that a 500-meter tall building is somehow considered to be permanent everywhere in the world. So no one is actually considering to demolish the Empire State Building or the Sears Tower or Burj Khalifa or so on. But there are more speculative interventions in the range of 150 to 200 meters tall that are going to be stay there maybe for 20, 30, 40 years, and then they will reach the end of their usable life, and they will either have to be converted or demolished and transformed into something new. So we were mentioning before the importance of the impact categories. We've been hearing this morning a lot about embodied carbon. Carbon is basically produced and released during the production process of the materials and during the transportation phases of these materials through the consumption of the fuel that goes into the factory that produces either the concrete or the steel and into the diesel that is burned by trucks. An important thing, though, to consider is that carbon is also released during the chemical transformation of the elements that produce cement and therefore concrete. So if we want to be fair with the 2 main materials, concrete and steel, we have to consider this that goes into the equation. So if you go to a steel producer, he will say, Steel is more sustainable because it releases less carbon than concrete per unit that you're considering. And this is indeed true. However, if you go to a cement producer or a concrete association, they will say that cement and concrete is more sustainable because it uses less energy to be produced. And this is also true. So we cannot decide. Life cycle is very complex. You have to consider so many indicators: water consumption, natural depletion of natural resources. You have to consider the impact on the humans, so on the health of the humans and on the animals and the ecosystem and so on. Of course, this is still very, very debated in the industry. This morning we just heard speaking about carbon. We decided that also energy has to be included into the equation. So basically, the research that we are doing is based on two different indicators. One is the impact categories is the natural environment, for one, and it basically indicated in global warming potential, which has a very, very difficult definition, but basically is the release of greenhouse gases into the atmosphere. But we're also including the depletion of the natural resources through the assessment of the embodied energy. They're both very, very important. Carbon emissions are considered to be the main cause of global warming and environmental changes. Natural depletion and the acquisition of energy and other natural resources is the main cause of wars, of international disputes, and so on. So we thought that these two impact categories have to be assessed equally. I just want to present, I'm not going to present any actual result, because we are still waiting to have some data on the construction phase and on the recycling phase for some of the materials. So it will be not fair and not complete to present final results. But we can still think about some issues and give some guidelines somehow for the design of future tall buildings. So we always think that tall buildings are less sustainable than low-rise building because they use more structural materials in order to be built. This is actually not really true because, as we said before, and as Don, I think, mentioned before, a very large part of the materials that goes into the structure of a tall building is not for the vertical structures, but is for the horizontal structures. And this is even higher if you include the foundations. So what can be done really from structural engineers and designers is to think about and conceive better flooring systems and reduce the lease span of the building. Longer is not necessarily better. Also, we have been told that steel structures are more sustainable than concrete structures because they can be entirely recycled. This is also not true because approximately 50 or 60% of the materials weight, even if in a purely steel building, usually goes into the concrete slab that creates the horizontal system. So again, what we need to do is to convince the material suppliers to find alternative floor system, and we need to improve the recyclability of concrete, because this is also very important in purely steel buildings. And finally, we thought originally that the transportation had a huge impact on the LCA infrastructure. This is, again, not true, because according to the study, less than 5% of the total emissions and total embodied energy used by the building goes for the transportation. And a significant portion of this, about 80%, happens in the last 50 kilometers. So it really doesn't care if the steel is coming from China or from Brazil and the concrete is crushed thousands of kilometers away, as long as it's transport to the site with trains or ships. Everything happens in the last 40 kilometers, and in all cases that we studied, this transportation happens by truck. So before conclusion, I just wanted to, well, there are some other initial conclusions. I just wanted, you can find them on the paper. I just wanted to thank all the individuals that contributed to this research and that will contribute to the next steps of the research, because without their support, this analysis would have not happened. Thank you so much.